So we're going to study the continuity of a piecewise defined function. So here we are given a function g of x defined by four parts. The four parts are the following: the linear function 1 minus 4x for any x is less than negative 5. Then the quadratic function x squared if you are working on the interval from negative 5 to 1. And then this is the singleton point here. If x equals 1, then y equals 1. And finally, the fourth part is going to be a linear part, 3 minus 2x, for if you are working on the interval for any x is greater than 1. So remember here, to look at continuity of a function, we must look at those, because we are dealing with a piecewise defined function. If those points we are provided here, which are x equals negative 5 and x equals 1, are within an interval, not at the end point of an interval, within, we just have to look at the nature of the function, which here are all polynomials, so they are all continuous. But if we're looking at a point where we are at the end point of the interval, which is the case here, the cutoff is at negative 5 and then at 1, then we really have to go the 3 steps here, which figure out if the function is defined, mean there's no open circle. If there's an open circle, there's also a closed circle. The limit exists when x approaches a. That means that there's no break in or jump in the graph. And finally here, the third condition, which, sorry, that's the one I cannot fix it, means that the graph is heading towards a point and it actually get there. So we're really going to have to look at what's going on and do that for all the 2 points we are provided, which is x equals negative 5 and x equals 1. So at x equals negative 5, I'm going to look at f of minus 5. Sorry about that. So what is its value, right? So remember, we have to go through step 1, 2, 3, right? So this is step 1. What's the value of the function at negative 5? So we look at here what we have. Let's see where that point x equals negative 5 falls into which intervals. So here we see that negative 5 is right here. It shows it on 2 intervals, but as you can see, it's never included. This is for any x's less than minus 5, so to the left of negative 5, and this is for this rule x squared is valid only for any x's from negative 5 to 1, but negative 5 is included. So you can see there's negative 5 is not included in those 2 intervals, and definitely not in the other one, because like negative 5 is not greater than 1 and negative 5 is not 1. So what does that mean? That means that the function is undefined here. So because the function is undefined at negative 5, that means that the function f of x, g of x, sorry, not I call it g here, so let's be consistent. So that means that g of x is not continuous at x equals negative 5. And remember that as soon as one of the condition fails, that means the function is not continuous at that point. So we don't have to go any further. I don't have to check the other 2. So I'm going to go through the same kind of processes for what's going on at x equals 1. That's my next question. What's going on at x equals 1? So again, the first thing I have to check, the first condition is figure out if the function is defined right there at 1. So meaning is, what is the value of the function at 1? So what is g of 1? And so once more, what we have to do is figure out the interval in which we work with. So here it's x is 1. And then you can see here, if x is 1, this is right there. if x is 1, the value of the function is actually 1. So we know that g of 1 equals 1. You're going to say, wait, but what about the others? Well, see again, once more, see that 1 in the second and the last parts here, the 1 value is not included. So really, we only have one value, is g of 1 equals 1. So the first condition is satisfied. So that means I have to go to the second condition, which is figure out the limit right there. Right? So we're going to do that. Let's look at the limit. But here it's going to be as x approaches 1. Right? So I have to fix the a. It's not a, but 1. Right? And it's not f, but g. So we need to look at this. That's what I say. I have to check this, see if it exists, and if it exists, what's the value? That's basically what I have to do. All right? So how do I go about it? Well, we normally do a direct substitution. So we look at the problem, and this is very important. Remember that when we are dealing with a piecewise defined function, which is the case right there, if you're looking at the limit as x approaches a number, and that number is a cutoff, that means before and after the function is defined differently, then you do not have a choice. You're going to have to check the one-sided limit. Because remember, this notation means that you're going to have to look at what's going on for the graph when your approach is 1 from both directions. But you can see here from both direction of 1, meaning from the left, that means you're looking at what's going on when your approach is with x is that slightly less than 1. And then from the right, you're going to look at what's going on for x is that slightly greater than 1. You see the functions are defined differently. To the left, x squared. To the right is 3 minus 2x. So here, I'm going to write that we must look at the one-sided limits. And again, the reason is because x equals 1 is a cutoff, which I know is not really, mathematically speaking, very proper, but you understand what I mean. So I'm going to look at the limit from the left. So I'm going to look at the limit from the left of the function. And then, so that means from the left, right? That means you are coming from the left, means slightly less than 1. So again, it's just a matter of which of the function here rules I'm using. Well, it depends on the interval. We are slightly less than 1. So definitely those two things are not working. You're going to say, well, should I use either one? Could I flip a coin, choose both? But remember, when you look at the limit, you are getting really close to x equals 1. So that means you are really only in that interval from -5 to 1. So that means that the only expression, the only rule that works is going to be the x squared rule. And now, because it's a polynomial function, you just do a direct substitution. Actually, here you plug in the actual 1 in there, and you get that the left-sided limit is 1. And then you're going to do the same thing. You're going to look at the limit as x approaches 1, but from the right. So remember what that means. That the notation for right means with a plus after the number here. So from the right, I mean slightly larger than 1. So here again, you have 4 rules. But there's only one that works. It depends on the interval you are working with. And because here you're looking at from the right, that means you are taking x numbers that are slightly bigger than 1. So that means you are working on the last interval. So that means the expression for g of x is going to be the last one, which is the linear function 3 minus 2x. All right, I'm going to just delete that. My plus doesn't look like a plus. So it's going to be 3 minus 2x. And now you're going to do a direct substitution, so you're going to replace x by 1, and that's going to be 3 minus 2, which is 1. And because the one-sided limits are equal, that tells us that the limit as x approaches 1 of g of x is equals to 1. And then the last points I must check is that the limit as x approaches 1 and the function at 1 the value must be equal. Well, we saw g of 1 is 1, and then the limit is 1, so that is true too. G of 1 so here g of 1 equals the limit as x approaches 1. So that means, in conclusion, that means that the function is continuous. So g of x is continuous at x equals 1. And we could check here if we wanted to. If I were to quickly really graph the function, so it's going to be a not perfect graph, but if we were to quickly graph what's going on here, so at so to the left of -5, the function is linear, and